So now, after like all those two presentations that were very broad, I will dive into really like a very technical topic. So I hope you will follow me. So this talk is about predicting the long-term behavior, mechanical behavior of animal glues using what's a so-called time, temperature, humidity superposition. And I want to highlight something here, that by long-term mechanical behavior, I'm not looking at aging. I'm not looking at chemical aging. We're really looking at the material response when stressed by loads that have different speeds, different rates of application of this load. And I'll explain. So first, animal glues, I will just highlight why we chose this material as a material to develop our theory or to test our concepts, because it's really what I will be presenting here. So gelatin is a very common material found in the collection. So it's extracted, as you might know, from a very structured material, collagen, which has this three helix structure. And when you apply the chemical treatment, heat, you obtain these random coils, the gelatin, which when they recombine or dry, will try to recover this well-structured material, the collagen, will not do it perfectly, and that's why you, in general, obtain a semi-crystalline material. And it's found in many of the collections. So it's used as an adhesives. Here I'm showing adhesive for joints, for example, in furniture. It's used as a sizing material in painting, easel paintings. Also as adhesive, for example, flaking paint on wall painting. So it's a very common material. And why is it important to look into it? Because this material is, as we know, very sensitive to temperature and relative humidity. And that's why we have this material that's whose properties are really dependent on the sort of, the conditions at which you measuring it. So here I'm showing, for example, a previous study we published in 2022, where we were like comparing, like glues that were available to conservators, from rabbit skin glue, hide glue, even different type of fish glues. And you can see how the storage modulus, which is the stiffness, was dropping as you would increase the humidity. So we can identify that way those phases, going from a glassy phase to rubbery, even to melting. But that's not the only thing that gelatin is sensitive to. Another thing that's important, yes, and it's important it's important to know those properties, because this information, knowing those properties are different in different ranges in environment and condition, helps you better understand then how an object behaves. It helps feeding those computer models. And here I'm showing one example among the many other studies that have been done mainly on easel painting, but also like we'll see during this conference on panel paintings. But you can really then better inform those models. But something also, and that's where my presentation is going into, is the fact that those materials, I mean animal glues, but actually a lot of polymeric materials have also have properties that are dependent on time. And by time, I mean the response to a stress that's applied. And this is because of stress relaxation. Those materials relax. There is, when we apply a stress on those materials, a relaxation that's occurring at the molecular level. The sort of the molecular polymeric chain are reorganizing themselves, and that's why this is occurring. And this has a big impact on properties that are measured. This stress relaxation results in what we observed, and that's very theoretical. It is not applied to all material, but often when you, for example, increase the loading rate at which you measure a material, you will see an appearing decreasing strain at break, as well as an increasing stiffness. And that's all related to this relaxation of the material. When you do a very slow test, you allow the material to relax to the stress that's applied. And so, as you can see, this is capital information. That's very important information, because the data that were retrieved from publication are really dependent on the way the material is tested. And this is really important and highlighted for those viscoelastic material. And that's why that's the case of gelatin, and that's where that's why the study was conducted. So when you think strain rates, the immediate correlation, it's not only like the scientist interest who wants to test his material. The direct correlation is stresses that are undergone by materials when they are exposed to climate variation. When I'm thinking of a slow application of stress or fast application of stress, I'm thinking of climate variation, for example, between a daily variation that are very fast changes in humidity and temperature. I can show you here an example from an external climate. So you can see that within a day or 12 hours, you see those jumps in humidity, but also slow variation that are associated to seasonal variations. So just to highlight my points. So the daily variation, it will be like stressing the material very fast. But in comparison, if you have a seasonal variation, it's like using this stress that applied very slowly. And so here, the properties, if you would have to model that and identify risk of damage, for example, in your objects, you know that if the mechanical properties you're putting in your model are wrong because you haven't put the properties that are really related to the rates of application of the stress, this can actually screw up your model. So how to then measure mechanical properties of a material that would be undergoing a stress that would last for 3 months, for example, which would happen, for example, for a seasonal change. There is some test you can do in the lab. You can test your material apply a specific load for 1 hour or 1 minute or 1 second. That's okay. But when you have to do a test that would last for 3 months, that's not viable. You cannot do that in the lab context. And there is a way actually to access that longer time, to predict this long-term behavior. And this is what is the so-called time-temperature superposition. This principle states that actually you can extend beyond the frequency of the instrument range, you can extend the prediction by increasing the temperature at which you're doing your test. And this kind of easy to understand because as you increase the temperature, you accelerate molecular movement, reorganization within your materials, and therefore it's like kind of predicting or seeing what would happen in the future. And this is like really, it's done in the polymeric industry. It's done to test material to predict their long-term behavior. For example, tires on cars, this sort of thing. So they would be tested and the prediction would be built. And you can see here the sort of direct correlation between frequency or rates of application of a load and a temperature, for example. So that's not something that's new. I talked about the industry, but that's something that has been used in the past, but very sparsely in our field. I think one of the first study was in 1995 by Marianne Nodliha, and her team, who looked at bending, and it was a painting, so fabric-supported paintings. And then more recently, we have from CCI, Eric Hagen, who had been looking at different paints. So here he was looking at failure strain. So that's 2 examples. There is also a more recent one that was a collaboration with actually the team of Lukáš and Sonia Budyok, where we looked at gesso. But let's go into our testing and I'll explain a bit better how this sort of concept was then applied to our sample. So we used one type of animal glue, actually, rabbit skin glue. We poured this 4% solution, aqueous solution in Petri dishes to obtain those nice films. And then we used the DMA, so dynamic mechanical analysis, that was presented by Emma. And we applied a sweep in frequency between 0.1 and 10 hertz. So it's equivalent to the load rate of how you would be testing your material. And then we did the test at a fixed RH, and we did this sweep by increasing the temperature from 15 degrees Celsius to 80 degrees Celsius. I'm showing here because I understand this technique is kind of not really known by everyone. So dynamic mechanical analysis, we saw it in a previous picture by Emma. So you can test your sample in different configuration. Here we tested it in tensile, in tension. And we apply actually an oscillation stress, and we look at the response of the material to the stress. So from this, we can take, for example, we can measure the stiffness of the material. We can also measure how fast the material responds to the stress that's applied. So you can really access the viscoelastic properties of your material. And here I'm showing the protocol that was used. So to ensure equilibration, we were doing 5 degree steps in the temperature and equilibration of 1 hour. So let's go to the data itself. Here are the different sweep in frequency that we applied. And you can see you have the different temperatures, and you can see how the storage modulus, or stiffness, that's the same thing, varies. And we will apply then the time temperature superposition. You can see how we can build then this prediction. It's and the superposition work. So you can, from there, you can calculate, that's something that's important, the shift factor, that's this AT factor, and you can measure that for the different temperature. Why am I mentioning this? Is because this fitting is not random. It's not only just by looking how smooth the curve look. By using those shift factors, the AT, you can measure actually the activation energy of your transition. And this is a way you can find those values in the literature, and you can kind of guess how well your fitting has worked and confirm that your master curve, your time temperature superposition master curve, how good it is. And we check that for all our master curve to make sure that the values we would obtain fit the literature, or at least we're in the acceptable range. So here's the master curve, and and then you can see how we can correlate the frequency with the time of application of a load. So you can see from second to even a year. And this is super powerful, because then this data that would be useful for computer modeling is accessible. So that's one thing. But the issue is that sometimes your material, even if you would do this extension and access this wider range, there is some limitation. And something that we wanted to use, and we also found in the literature, people not only have been using time temperature superposition, but they've been using humidity or moisture content, moisture, also as a sort of plasticizer to accelerate these processes of reorganization of the matter. So, and it's something we wanted to explore as well. And so we tested our glue not only at one fixed RH and range of temperature, but we also varied this humidity to access even beyond, for example, the room, the 50% RH and 20 degrees Celsius fixed condition or normal conditions. And this is because actually when we did our study before, in the past, looking at those sweeps in temperature and humidity, you can see how, interestingly, there is this correlation between the material what's experiencing in temperature and humidity. And you can see how those curves superimpose, and we can highlight the transition, the phase transition in the material. So let's go to the RH scans. Here you can see the 3 master curves that we built for the different humidities. We had 70, 50, 30. We have the storage modulus, so the stiffness, as well as the loss modulus that's related to viscosity of the material. And when we actually slide those curves, we can see how more or less nicely we can obtain this master curve. And here it is. So this helps to really expand the prediction beyond what's feasible in the lab. And if we had to make an interpretation, that's the sort of thing we could draw from those type of curves. Like you can see how the stiffness, for example, of your material could change between a stress that would be applied over a day or over a year or a month. Of course, you might not be interested in knowing what's happening over a year. And you can measure other type of properties here. You could measure like strain at break. You can measure bending. So here, I don't want you to necessarily stick to this 65% value. It's not necessarily what the highlight of this presentation. I think what we want really to show is how important it is to measure this long-term behavior of material, or how these mechanical properties are affected affected by the way it's measured. And it's something that could be used more maybe in our field to better inform models, computer models. So if I had to conclude here, I hope that this presentation showed that really like the use of DMA and thermal technique can really inform better and facilitate systematic evaluation of adhesives, and also support the modeling and prediction of risk of damage. I think in the future, because we will try to improve maybe the time moisture superposition of our master curve. Something we realized as we were building this master curve is that it's not an easy process. There's a lot of things occurring beyond just increasing the temperature. There is, for example, as we increase the temperature, we're also drying the material. So the moisture content is changing, and this affects the properties. So there are things we want to explore and maybe use time moisture superposition, because we might have a better idea of what is the material we're looking at to predict the behavior. And yes, and also we will reevaluate the expression of those shift factors. That seems to be one of the key elements in designing those big master curves. And I want also to thank by people I could talk to, because it's not something that's easy. So Marianne Oudliha, of course, of the Birkbeck University of London, and John Duncan, who was one of used to be at the Lacerta Technology, but he's the designer of those DMA with RH control included in the temperature to control. So that's it.
Thank you very much.
Thank you.
Question? Cecilia.
Hello, I'm Cecilia Gauvin. I thank you, Alexandra, for your presentation. It's very interesting. I've been working myself a bit on that. I never published, as I never published anything. But I wanted to, on your future work, maybe if you go back on your conclusion slide.
Sure. Yes.
Yeah, I had a question exactly on these shift factors, because basically it's based on Arrhenius law. Do you think you need to reevaluate Arrhenius laws to be able to change your shift factors? Because I know that it is actually, you need to work on the initial model, which is only taking into account the temperature, to be able to have a comprehensive master curve for RH change, right?
Yeah. So no, it's true. The shift factors, there's different equations that you can find. People have been designing those equations because they all started with the Arrhenius or the WLF, the William Ferry. So there's different ways of expressing. And it's true that limiting it to just temperature has been reconsidered. I found some equations that were fitting for one type of material. What I'd like to do is like checking that this would apply for our gelatin, maybe improving it. But it's true. It's one of the main thing I will be looking at to improve these models, because it can change drastically sometimes, this superimposition. It's beautiful on the paper, but the reality is much more complex. And that's why I think we really want to look into time moisture content, because we would be able from differential vapor absorption measurement to access the moisture content and know exactly what we're looking at. And so we hope that it will improve then these models and designing us. But we will try to put everything in a paper, and at least you could be very critical about how.
No, I don't worry. Thank you.
Yeah.
Other questions?
Sure.
Hi, my name is Beril Baysır-Simser. I have a question regarding, you are looking at the rate. Are you looking at the history of application of rate? For example, you are going from 1 to 10. Are you also considering from 10 to 1? Because we know the history will change the behavior as well.
You mean 1 to 10? You mean
in terms of the application of rate?
The frequency of application. Mm-hmm. No, I did not. We did not think of looking the other way around.
Because
that could be something to look into.
Daily, it is higher rates applied, and then you are summarizing it to lower late applications. So it might be interesting to turn them around.
You mean looking in the shorter term of faster rate of application?
And then go slower versus slow rate to higher?
Yes, I mean, I don't know if it would change the curve, the results, but I mean, I haven't thought about it. I could look into it. I could look into it to check the response I would get. Yeah.
Thank you for this question. Who else would like to ask a question? Alexandra?
Maybe if people from modeling would find it interesting to get this.
Alexandra,
Yes, tell me.
I have the question.
Sure.
So, do you think there was a paper which I obtained from Aaron yesterday or a few days ago showing that glue ages, how the chemical aging of glue would change that behavior because we are testing a new?
No. It's totally true. There's the aging, the chemical aging. There's also the sort of relaxation the material is already undergoing. I mean, that's the thing with glue. There's also how it's been dried. That's where it's becoming some sort of, big data bubble because, I will not start on this but it's true. It's something that should be investigated. But again, we will need a sample that would be representative. I think most of the work we're doing, we're not trying to say, okay, this material has those properties, this material has those properties. We're trying to understand better the range, sort of range of behavior, and at least we know it will not go beyond this range. So at least it can then, if we do some sort of modeling, you know that you cannot expect the glue to have the behavior of PMMA, for example. It's within this range of properties. So
I just asked to keep the discussion, but I have to say that I'm using the Alexandra's data, for example, when we are extending the mechanical model for canvas paintings, for panel paintings to the hot and humid climates. Without your curves, it wouldn't be possible. So it's very important work. Maybe Stefan and Vince?
I'm really going to give a question which I anticipate that Matteo Rossi Doria would probably ask, because the last time I spoke to him, he was very much concerned with the fact that our literature is woefully ignorant of the fact of bloom, and that different glues with different blooms have very different mechanical properties, and that's well understood in the food industry. And he is convinced that some of the old masters 200-300 years ago understood bloom, not necessarily the measurement itself named after Mr. Bloom, but what it actually implied, and to select different kinds of glues. So I assume then you know the bloom of the glues you've been looking at.
Yeah, I mean, they were like, we didn't make them, so actually it was provided. I mean, you could buy it by the manufacturers. Yeah, but I agree. I know that we had discussion with Arlen here. It's all this. I mean, even the bloom. I feel it's not. A glue cannot be defined for me only by the bloom, because it's really a measurement that's done under specific conditions. But that's something to be discussed.
Yeah, so I very would love to comment. It's not a question at all. I'm sorry. Just a comment, because when Alexandra was speaking about this difficulty in having representative material for the testing, then it's very interesting to think about possibilities as using the same type of a technology, which is a dynamic mechanical analysis, also in our micromechanical study with indentation, when we can actually access the information about the stiffness of the materials during the probing the sample with the nano indenter. And in a way, it can give us some information about the relaxation of the historic samples taken from the object. So we are not there yet, but that's an interesting opportunity, and Alexandra's work is showing the path forward for creating the master curve, which will be applied in the different scale in geometry.
Yeah. If anyone has more insight into master curve, I'm happy to discuss and exchange, because I'm still working on it.
Alexandra, can you comment, because I know the paper about difference between fish glues and mammals glues, and how it impacts the preference of the for example, conservators using the glues to consolidate objects in the cold climate, for example, the wooden churches in Norway.
Yes, I mean, So I think there is some information that's already known. I mean, we know that there's huge differences between mammal glues and fish glues. And it's in general because the fish glues are more sensitive to humidities. But then there's also this difference in the fish glues between the one from warm water and cold water. And so the warm water fish, actually, gelatin, is behaving more like the mammal glue gelatin. So much more resistant to humidity. So in terms of temperature, it's often more related to how glassy it would be. And then again, it's maybe like the same comments you made, Stefan, about acrylic. It's like, we know it will be glassy, brittle. Then will it crack? There's probability it will, but then I guess that's where this exchange with practitioner, would they have a better understanding sometime how it behaves? This choice says that's how it's made. But that would be my broad answer.
Still some time for one question. Daniel, please.
Yeah, hello. Thank you very much for that really nice scientific investigation. My name is Daniel Konopka. From Dresden, and I normally do numerical analysis, and when I find such kind of glue, it is in a bond line or part of the gesso or whatever, and then we see it has totally different mechanical characteristics than the glue itself. So, but that's what I'm interested in. Have you any idea to how to come from these data of the pure material to the characteristics of a composite, maybe?
So can you repeat what do you see? What the difference you see between the bloom that you're given and the properties? What is the difference?
When we have the characteristics of gelatin glue, it behaves different than when it is applied to a bond line with the two adherents, and it has somehow other characteristics. It's not that viscoelastic anymore. But I would be interested to have the data of the bond line.
Yeah, I'm interested as well to see exactly how it behaves, or what you've measured, or what you kind of different. Because it's true that most of the tests we wanted to simplify the system, so we were using film. You could see, but I can see the limitation because you see it actually when we prepared it in Petri dish. The substrate on which the film is deposited has a huge influence on the properties. That's an added thing. So that's why people would put it on glass or on a plastic, depending of how restrained the substrate is. The reorganization of those single strands will be different. And so then the crystallinity will be different, and then the properties will be different. So yes, it kind of makes sense to me. Doesn't come as a surprise, but I didn't start to look into this. But that will be interesting to see your data. Yeah.
Marco?
Yes, thank you very much for your presentation. Just a comment. Some year ago, we had a PhD work where we made an examinations of several artworks, and we study the composition of the different glues, the type of glues. And maybe it is interesting for your work to know that the choice of the glue was made also according to the size of the pint. Larger the pint, change the glues. As in larger pint, they use casein-based glue, because of the open time. You know what's open time when you made a gluing process. You need time before the glue start to react. In larger pints, they need more time for gluing the boards. So quite big pint, at least, let me say, in Italian school pint, because it was such kind of pint that we examined. We found a systematic use of casein for larger pint than animal glue that was used in smaller pints. It was just a comment.
Yeah. Thank you so much.
But I think that it's absolutely good starting point for the research on the glues, and we have the reference point.
Well, and by the way, I should, because we wanted to start, if people are interested in glue, I'm happy to kind of create this group of glue fanatics. Now, because we started it and we abandoned the idea, but we should revive it again.
Thank you very much.
Thank you.